Hi, and welcome to our 129th test and measurement video. Today's topic is harmonics and other anomalies in electrical power systems, causes, effects, measurement, and mitigation. We'll be using two instruments, the Tektronix MDO3000 series oscilloscope and the new Fluke 438-2 motor analyzer. To the musician, harmonics are beautiful. They extend the frequency spectrum of many instruments, and, isolated from the fundamental, they have an eerie, glassy quality that is used to great effect. To industrial electricians and engineers, harmonics are always objectionable, resulting in overheating of conductors, shortened motor life, and wasted energy. Utility power in the United States is available in a range of voltages at a frequency of 60 Hertz, or what used to be called 60 cycles per second. In many countries, the standard is 50 Hertz. For some loads, such as incandescent lighting and resistive heat, the frequency isn't critical, but induction and synchronous motors and transformers may overheat with shortened life if operated at the wrong frequency. These loads thrive on a nice clean sine wave. In theory, that's what they receive from the facility power outlet. A sine wave, as opposed to square wave, pulse DC, triangle wave, or some other waveform, is produced by an electrical generator due to its rotary nature. On a utility scale, this is ordinarily produced inside the housing by three windings precisely situated 120 degrees apart. This three-phase power is distributed over a 3 or 4 wire system and supplied to facilities that require three-phase power. For individual homes and small commercial customers, single-phase circuits are picked off, with every effort to maintain an overall balanced load. Utility operators closely monitor the quality of their power output, looking for voltage and current imbalance among phases, frequency drift, dips, and swells in harmonics. How do harmonics enter this picture? To illustrate, we'll display a utility waveform in the Tektronix mixed domain oscilloscope. Taking care not to connect the probe ground return lead to the side of the line that is referenced to, but floats above, ground potential. Then we switch on the channel and press auto set to get a stable display. There are no obvious harmonics, but it is not a very pure sine wave, lots of noise today. To verify the non-presence of total harmonic distortion, THD as it is known, we can easily hit math, followed by FFT, to see the utility signal displayed as power in the frequency domain. As you can see, there are no discernible spectral spikes, just the eternal noise floor. Harmonic distortion is strongly influenced by the load, especially if it is close to the measuring instrument. I am starting up a fairly new electric drill which has a universal motor. Notice that the waveform is essentially unchanged, except for a slight dip on starting. By contrast, here is an old clunker, probably with worn brushes. Notice how the utility waveform is severely impacted, sometimes even to the extent that the oscilloscope's triggered sweep is disrupted. Now we turn to the Fluke 138.2 motor analyzer. This is the latest of Fluke's superb power and motor analyzer instruments. It has the full functionality of the previous 435.2 power quality and energy analyzer, and additionally, you can attach the voltage leads and current coils to a three-phase motor while the motor is actually in service to obtain a full picture of its condition and efficiency. Owners of the previous 435.2 power quality analyzer can download an upgrade from the Fluke website to add motor analyzer functionality to the instrument. Full documentation includes specifications and user manuals for both instruments, and these are available from Fluke and can be obtained free of charge even if you have not yet purchased the instrument. The Fluke 438.2 motor analyzer, like the power quality analyzer, is a handheld, battery-powered tool, so you don't have to worry about exposing it to a dangerous arc fault, as with an AC-powered bench-type instrument if connected to a voltage that is referenced to but floats above utility ground. The enclosure is impact, moisture, and dust resistant, so there is every reason to believe that with careful handling, including observing voltage limitations, it will last indefinitely. Of course, some kind of load is required for all measurements in order to get a full picture of the quality of the power source or the condition of the motor. To prepare for a motor measurement, the first step is to consult the motor nameplate. To comply with the National Electrical Code, all electric motors, except small clock motors and the like, are required to have attached metal nameplates displaying information applicable to the motor. To begin a motor analysis, open the motor setup screen. On the motor analyzer keyboard, open the motor setup screen. On the motor analyzer keyboard, press Menu, which opens the menu screen. Then press F2 to change to page view. Use the up and down keys to move through the menu selections and highlight Motor Analyzer. Press Enter to open the motor setup screen. Use the up and down and right and left keys to enter the nameplate information. The Motor Analyzer supports motor designs based on NEMA and IEC design types. If the design type is unknown, press Other. In this event, you must consider an additional error of 5% for the mechanical motor parameters. Default values are available for the nameplate settings and ranges. Use F1, Unit Setup, to open the setup screen to configure these values. The selection depends upon the default motor frequency. The function keys guide the user through the screen setups. Press F1 and select the Unit Setup screen to open the Motor Analyzer Function Preference screen. This permits the user to select metric or imperial units for the mechanical motor power, torque, and default motor frequency. Press F2 and select Trend Setup screen. This permits the user to adjust the duration of automatic trend recording. The default is 7 days. Press F4 and select Defaults for the motor setup screen. This permits the user to set the default values defined in the Function Preferences screen, included in the unit setup. The defaults depend upon the motor frequency. Press F5 to start measurements. This starts the motor analyzer function. To measure power and motor quality, begin by pressing Menu. The different measurements are volts, amps, hertz, harmonics, power and energy loss calculator, power inverter efficiency, unbalance, inrush, and monitor. In the menu screen, each of the measurements can be performed and accessed by pressing Enter. The volts, amps, hertz screen displays volts RMS for Y or delta configurations. To leave a measurement, press F5, which is associated with Stop, Start. Then you can discard and restart, save, or cancel. To move on to the next measurement, press F1, which is associated with discard and exit. This brings you back to the menu screen. Use the down key to highlight other measurements and press Enter to begin the measurement. If volts and amp cables are not connected to a motor or power source, the instrument will assume the inputs are 0 and record the measurement on that basis. When you go to unbalance, notice the phantom volts in the polar chart. This is similar to the noise floor in a spectrum analyzer. In this screen, you can use the F1 key to choose between volts and amps and among L1, L2, and L3. Thanks for watching. New videos are added periodically, so check back frequently.